Sure. So I'll be talking about open source database architectures, and typically therein what we are trying to do is we have a huge landscape of databases. So we try to make sense of what databases are there, what are the different components around those, and what are those simple Lego blocks as in concepts which are quite similar between all of those. As I went ahead and made my slides, I realized this is a huge talk, so I kept cutting. And I was afraid that maybe is the essence of the talk getting lost. So maybe I'll do whatever I can here. I have practiced it thrice last night to make sure it lands up in time. But hopefully whatever I can cover today, I'll cover, and then the remaining, if you are interested, we can have a chat offline. So I am a regular software developer who happens to love open source and databases and streaming systems in general. Distributed in those even better. I had the CPaaS data platform team at Nutanix, and previously I was employed by MySQL, working in the MySQL application team. That was around 2020 to 15. A couple of times I presented MySQL here. In fact, my first external talk was here as well. After that, backend services, data platforms, and I have been a contributor in MySQL because I was working there, of course, and Pulsar code bases. Regular speaker at meetup. This is my 19th talk in a conference, and I also organize some meetups around database architectures and ecosystem. Couple of them were at Nutanix, and one in the Flipkart office across Apache Pulsar and Apache Druid. This is just a journey that I am getting started on, and hopefully a lot more people join the community and we can go ahead learning from each other. So while there are a lot of database, let's start with something very simple where we say these are the components that typically make a database. I mean, databases are sort of huge in numbers, are very different, and we will have a look at some of those varieties. But let's start with a simple system. A typical database would have a transport system, which is basically around how the client application connects to the database server, or the other part in the transport could be how the database servers on different nodes talk to each other and what are the protocols they use. Then your query goes to the query processing engine, where you have your query parser. Once your query is passed and declared correct, then you send it to the optimizer, where optimizer has some options, and among some options it uses the best given your storage engine and type of query you are firing. It will sometimes rewrite your query in ways that is more efficient. It has some knowledge of what database you have, and in this case what could be a better way to query, right? So make the efficient plan. If you look at the plan, that's an output of optimizer. Execution engine, again it could be like a very simple case, local execution. You have one database server and that returns. The more interesting case for me at least is the distributed databases, where then you have to talk to each other among peers, leaders, followers and stuff like that. So we'll go through this a little bit in detail, and then finally the storage engine is where I am most interested. My expertise is more on storage than networking, so I'll spend some time there. I'll very quickly touch transaction manager and log manager. Access method is something that is very interesting to me. Access method is basically saying that so if you look at the database landscape, if you know Postgres, this is referring to table access API. If you are familiar with MySQL, this refers to the handler-turn interface. Basically what happens is, behind this interface you can plug in different storage engines. Like in MySQL the default is InnoDB, but you could choose a different engine and plug it in there, and your database will have completely different characteristics. Buffer manager is basically something that we will also cover in some detail. Recovery is something that I'll see if I have time. I have it in the bonus slides at the end. I'll try to cover those. So I'll skip query processing for today. Maybe in a future talk I'll cover that, and the other three pieces I'll try to cover in some detail, and if time permits at the end I have some architectures of real world databases which are used quite a lot, and we will go looking at specific concepts we have learned to look at how those are being used in the production grade systems today across analytics, relational, streaming and everything. So first off, transport like I promised, and in that we will start with the client communicating to the database server. First of all, you have to have a common language. If me and you have to talk, we have to agree on a language that we can talk on, right? That's the same with databases. You have a server, you have a client, maybe embedded in your application server, and how do they talk, right? So there are quite a few choices. SQL, I think most people would know SQL. How many of you have worked on a traditional SQL database or a relational database, MySQL, Postgres? Pretty much everyone. I expected that. So your conventional relational databases are MySQL, Postgres, Oracle, SQLite is an embedded one. Then you have analytics databases where you have ClickHouse, Druid, Snowflake in this list, but the list is quite big. So there also SQL is seeping in. SQL is actually also taking a lot of adoption in the streaming world, where for Kafka you have KSQLDB. If you're using something called Apache Pulsar, that's something I have been using for 4 or 5 years in production now. That is also coming with SQL. The modern streaming databases which are being written as of now in the last couple of years, they are starting with SQL as their first language. Flink has Flink SQL. So there is a huge adoption of SQL now, and it seems like every decade, somebody said this, every decade somebody comes up and says the SQL is crap, we will start with something else which will be amazing, and then towards the end of a decade or something, the SQL makes a comeback somehow, right? I can't credit the right person, I don't remember the name, but that's something I see if I look at the last 30 or 40 years history of 30, I think, not 40 now. It started with around late 80s or something. Then over last decade or so, NoSQL databases have been taking on. I remember around 2012 to 15, I used to be employed at MySQL, and MongoDB is coming up. It was the really cool kid on the block, which MySQL used to be in its earlier days. But NoSQL has done wonders to this ecosystem. Why do you need a NoSQL database really? Several driving forces were there. The need for greater scalability than relational databases can easily achieve. Basically, you can still do it with some caveats, some experts guiding you, some careful ways. You can still do it in MySQL databases, but I may be biased because I was working there. That's not the first job, right? We all have some soft kernels for our first jobs. If you have very large data sets, very high write throughput, then you typically are looking at MySQL, but that's not the only reason. If you need a specialized query operation which is not well supported, so what really happens is MongoDB came up with cool JSON API. Now it is eventually adopted in MySQL, Postgres and stuff. So there will be more, and it's better for the community that there are more query languages, and eventually they get adopted in a lot of different databases if they are popularly used. More dynamic and expressive data models. So if you hate the boundaries that schema forces you to put, in certain cases I think really the sort of document model of communication, this is an API and stuff, those are good, but that's not the only API, document API. And then regarding NoSQL, I feel like the name is terrible because I am Shivji, I can't call the next gentleman not Shivji, right? This is weird, right? And if I talk SQL, you can't tell me I am a SQL database. If I talk English, it's not like I am in English, right? So SQL is just a language, let's keep it there. NoSQL is actually a family of databases. So you have document databases in MongoDB, key value databases in Redis and Amazon's DynamoDB, graph databases, Neo4j, ArangoDB, Neptune, columnar databases, Snowflake, ClickHouse, Druid, and whatnot, wide column or column family databases in Cassandra, Scylla, Google's Bigtable, HBase. Towards the bottom, you talked of scale and distribution. You have now some databases like CockroachDB and Yogabyte, which support the Postgres protocol. So they try to become a drop-in replacement, but they are distributed in nature. So I mean, it's in my opinion, the name NoSQL is a little bit weird. If you are catering for distribution, specific query modeling or flexibility of schema, that's where I generally would think your database falls in. And then how can you complete a talk these days without talking about vector DBs, AI or whatever, right? So I had to mention these. Vector DBs in my opinion are also a class of NoSQL database if you go by it. For me, the interesting ones are Milvus and Quadrant. These are two I have followed for some time, and our good old elephant in Postgres, right? They have an extension in pgvector that you can use if you're already using Postgres and it serves your purpose. But it's a huge list of databases. If you want to look at a database of all the databases, pretty much all the databases, then you go dbdb.io and you can see that's a huge list minted by CMU if you're not mistaken. Now we looked at the query language, the way these guys talk. So we express certain things, but what is the query model and query patterns, data model and query patterns? If you look at transactional versus analytics, and you look at your own use case, which is the one you should go for, it's not as easy, but here is guiding sort of points that I typically use. This table is actually taken from one of my favorite books, Designing Data Intensive Applications by Martin Kleppman. It's there in my reference, I can't escape it. This is a book that I've read 3 times, and a lot of content here is actually inspired from there. If your main read pattern is that you are going to take out a row or a small set of rows from the database, like your Facebook timeline, right? For the user, you want all the details about the user, maybe the about us page of a website or something. Then you are looking for transactional database. If you are looking for an aggregate over a column, let's say, how many people here have used Grafana? Okay, some visualization tool, if not Grafana. If you are looking for specific piece of data and want to make an average or a sum over time on top of that, your query pattern is basically taking a bunch of values in one column and aggregating over it. Analytics database is what you are looking for. Your write pattern, typically in transactional databases, you're looking for random access built in the age of HDDs, and you're looking for some user aid bit. Maybe somebody on website is making his profile, so you're taking inputs and putting them all together in a row in the database. In analytics databases, generally people would advise you to insert in bulk, so bigger files. For instance, if you take a Druid or ClickHouse and try inserting one row by one row, it'll suck, right? Then if your data is in transactional database, it probably represents the state of the world from your view at this instant of time. More queries, more transactions, state of the world changes, but this for me represents the current state of data at this point of time. In the Facebook case, for example, current state of all my users would be in a transactional database. They use MySQL, that I know from being in MySQL in the early part of my career. In the analytics database, you would typically have historical events and some near real-time events. We'll look at the architecture going ahead. Generally, gigabytes to terabytes. It's fine to manage your relational databases. Beyond terabytes to petabytes, the NoSQL systems have actually in the last decade or so come a long way to make it easy to run your database. Object store there is a huge invention in my opinion, but that's where you would use analytics database. So we talked about transport a bit, query language, model, query patterns and stuff. Now we will talk about remote execution. Local execution is actually, there's not so much to talk about transport, right? We already talked of client communication, so now remote communication. And what better way to start the discussion than CAP theorem, right? The good old CAP theorem. Basically, Dr. Eric Brewer proposed it in 2000, and he said, you have these 3 things, and you can select only 2 out of them. And here is again Martin Kleppman's book and blogs. That's how he describes it. CAP, consistency and availability have very specific definitions, and the proof of the theorem will only work if you really use them carefully only in that meaning. Otherwise, there are so many interpretations, it's very easy to actually get lost. And CAP will not make you sort of make the final decision. It will start a discussion, and then there are more things that you can discuss around that. So CAP consistency is actually linearizable consistency. There are a lot of different levels of consistency, like serializable consistency is something that Postgres and MySQL of the world would support. Linearizable consistency means even though you have a distributed database on various nodes, you got to make it for your user as if the writes and reads are happening from one single database. What that means is laws of physics won't allow you to just write on a bunch of 10 nodes and make it like that, but for the user the illusion still has to be like that. And by the way, a very important note is one of the favorite interview questions that I ask when I take interviews these days is consistency in ACID and consistency in CAP. They are very different things. Consistency is CAP is linearizable consistency, applies across set of nodes, and it has to be sort of the same view, and I'll take a diagram to explain that. Consistency in ACID is, you should move from one state which is a valid state to another valid state. So you have those textbook examples. I am transferring from 10 rupees or 100 rupees from user A to user B, the total here should be the same total here before and after transaction, stuff like that, right? So single data copy is what we are looking at. If you look at this diagram, right, schematic, this is a description of a football match between Argentina and Germany. Germany scores and the goal. So Germany has let's say won the World Cup. So the referee declares a goal. We go to the leader database, the green box database and the arrows there. So here we are talking of MySQL and Postgres default asynchronous replication. We will look at other choices, but here what we do is we write to the database. We prepare to be very specific. We prepare the transaction. We send it to the followers, and then we say fine. We commit and hope that one of the databases will be able to commit the transaction into their storage region. So one situation that could happen in your common consistency databases would be that, you know, let's say Alice and Bob were watching the match together in a room. Alice goes to follower 1, and by that time it goes, the transaction has been written here. For the simplicity, let's say it's written instantaneous in the database. It gets here, and he gets the final score saying Germany 1, Argentina 0. Fine, great. Bob hears that, gets to sort of refresh his app and his or her app, and sees that score is still 0 because that transaction has not synced in follower 2, right? So this is a very valid case that would happen in your transaction database, and this is fine. This is fine in the practical system, right? But this is not consistent as per CAP, right? Because Alice has seen some score and announced that he has seen the score. Bob knows of this announcement, goes and fetches, still doesn't see. For the user, different states of the databases across nodes are not consistent as per CAP, but that's your favorite CP database, right? So CAP availability basically says that if you have a bunch of nodes in a distributed system, every non-failing node has to return a non-error response, right? Somehow this book's definitions are difficult to digest, so I'll try to break it down a little bit. So it's not sufficient for some nodes to respond. If you have 5 nodes, all 5 have to respond if they have not announced that they have failed. And by the way, CAP says nothing about the response time. So in practice, on your website, if the transaction takes an hour to return, it's still CAP available. In your practical case, it's not available mostly in your websites. Well, partition tolerance is just network cutting off. When we are talking distributed databases, you don't really have a choice. I mean, the network will cut off. In the age of cloud, you don't even know where it is, what is happening to it, and there can always be a disaster. So you don't really have a choice in this matter. To avoid it, you could probably have a MySQL or a Postgres system, one read replica, you just write to this one and stuff like that. But then you have either some data loss, or if you are using a synchronous application, or maybe if you just have one server, then you don't have the partition problem. You can think of consistency availability, but then you have availability problem, right? So what does CAP theorem really state, right? It's easy to visualize, and that's the proof of it, right? So let's say Alice was hooked up into data center 1 and Bob into data center 2. The network cuts off. You basically only have 2 choices. You can say that, you know, I will move all my users to data center 1, so my web app is available for everyone, in which case this guy has not failed, right? But it is returning non-error response if it is contacted, right? So you are not available in the CAP sense, right? But you are consistent because you only have one node, you are connected there, and everyone gets the same state. So every user sees the same state, no problem, consistent, right? Or you can say that I will continue to keep these users here and there, but then here you have inconsistent state. Alice and Bob in the same room, they know Alice has the updated score, Bob doesn't, violates CAP's consistency. Typically people call these situations as AP and CP because you have to support partition, you choose between availability and consistency. But I think it's a very weird way to classify a database. Given one database, change configuration, it will end up into another one. And if the consistency in my database and in CAP are different things, what's CP really, right? This is actually a huge discussion that I love to have. But in the interest of time, I'll go quicker and skip it there. If you are interested, I will be available mostly all day today. Let's have a chat about it. I love different opinions about it. Let's take the questions at the end. There's a lot of content. I'm sorry. So people have gone ahead, made corollaries on top of CAP theorem. Professor Daniel Abadi made this other theorem, Pesel theorem, if I pronounce it right. Basically what it says is, if you are looking so if you have a network partition, then we talked of CAP theorem, we choose between availability and consistency. If you don't, you still have to trade off between latency and consistency. What it means is that if you have a database server and follower databases or something, or peers, you are waiting for, you are using synchronous replication, you are waiting for response time from the other databases going over the network, looking for consistent state, means you are taking up latency, right? It would be much much less latency if you could just write the way we saw in the diagram. You write your own database, send it, don't wait for ACK, and quickly return back the commits. If you are writing to 5 places, maybe one of those would be there. And DynamoDB actually does a great job around managing those things. I'll talk a bit if at the end about it. But we've been talking about replicating data across different nodes, maybe across availability zones or something if you use cloud today, or even data centers. Then replication, why do you basically need it? Lower latency, right? If you have multiple copies of data, you can serve your user from the copy of data that is closer to that user's geolocation, increase availability and resiliency. So if you have multiple copies of data and one blows up, you still have the copies of data, you can sort of fail over people to other data centers or other servers, and then you are still available. If you have more nodes, more read and write queries can be served, so more throughput. And replication can be implemented in different forms, and there are real systems in each of those. It could either be a single leader, multi-leader, or leaderless, basically quorums kind of thing. So typically in your MySQL and Postgres of the world, or even others, this is a simple schematic of how the replication works. You have a leader database, you have the followers, you do a write. You can even put read and write both on the leader, and leader prepares the transaction, or in a sync it can also commit after it has sent the change log to the follower. We will look at the MySQL replication architecture to go deeper here, but basically what you are doing is you are saying, I have updated this table, this is the primary key of the column I have updated, and this could be an array, like these are the this is a primary key, this is another primary key that has been updated, this is the old snapshot of the row before update, this is after update. All of that you package and send over to the slave, right? Like I said about replication going deeper, you either choose asynchronous, semi-synchronous, or synchronous. I will talk a little bit through this diagram to give you some sense of what these are and how do you make the choice. So this is semi-synchronous for me. Asynchronous is, I have covered that a couple of times, but just sort of for completeness, you write in your own database as the leader, and to the follower you write, prepare here, send, commit, and hope that it will be replicated in at least one of those, but you don't wait for an acknowledgement. In fully synchronous database or a synchronous written here, you basically have, let's say, a leader and you have 5 followers. You are waiting for an ACK from all of my followers. The trouble there is that if even one network line is slow or broken, then you are not available, which is a very big deal. So there are workarounds to make it smart, and one of the simple things to do is semi-synchronous. What that means is, I have a leader and 5 followers. I am fine if at least 2 of those followers give me an ACK, and then I can go and commit, right? So I prepare here, I send it to 5 followers, any 2 out of them, if they can send an ACK, then I know that it's gone somewhere. So in the event of a failure, I can go collecting all the transactions everywhere, put it in one candidate that I want to promote in the event of a failure, and promote it and make the followers point to this new one. I'll talk about data recovery a little bit later, but what you see here is, so Alice updates profile picture, it goes to the leader database, leader sends it to follower 1 and follower 2, waits for ACK from follower 1, semi-synchronous replicas is one ACK, and then you commit. The other one could take time, and that's okay. And it could be any of these. In a different transaction, this blue line could actually reach here. This guy could acknowledge, the other one could not. So that's semi-synchronous for you. I said that when you execute a transaction on the leader, you have to send the difference that created on the database. Or there are other ways of doing it. Like, how do you communicate that transaction? You basically have to send it over the network. There are different ways to do that. Statement-based replication has been there in MySQL for very long now. You basically log the statements in that transaction, begin my statements, insert, update, whatever, delete, whatever, and then commit. That whole thing is written just like that, sent over the network to the follower. There are some cases in which it will fail. Imagine you have insert into the table some random number. It will generate something different on the master and different on the follower, so it will fail there. Insert into some timestamp column now, right? It could fail. If you are allowing writes on your follower, which MySQL by the way allows, so it's not a weird case, it's a valid case in a trusted database. Then auto increment columns could have different values. Triggers, stored procedures could be different on these leaders and followers, so that could become inconsistent. Wall shipping is used in Postgres physical replication, and Oracle logical replication is basically saying that, instead of writing all the statements in the transaction and sending those statements and being unsafe in the event of random generation inserted in the table, what I will do is so my database is in one state. When I do a transaction, it changes the state of my database. There is some diff that happened, right? Imagine git diff, right? Some diff that happened. What if I send the diff, right? And the same diff can be applied on the follower. You could be sending too much data. So MySQL's default is actually a mix of both these. So they have some statements like these, now and rand, marked as unsafe. In the unsafe statement case, it will use row based or logical replication, and in safe ones it will use statement based. So you have a trade-off there. They could also be trigger based. Triggers and stored procedures will give you the flexibility that you can write your own code there, own filters or whatever. But the really famous one for me that I have used personally is Debezium. It plugs into MySQL, Postgres and MongoDBs of the world, and then gets the changelog events from your write ahead log and sends it over as a chain stream via Kafka Pulsar or some streaming system, right? So that's great. Oracle's Golden Gate does something similar. If you think of multi-leader replication, you have typically across data center, if one data center 3 nodes, other data center 3 nodes, across data center you typically want to be async, otherwise the latency could be too much. If there are multiple leaders, the implementation, if you try to do it yourself, it's difficult to do, a little bit error prone. CouchDB is something that does, but for conflict resolution what it does is it gives you all the copies, and the application could select knowing the specific knowledge of the context there. Or we will look at the Dynamo case going forward. That's a great way to manage. Stressed examples for write everywhere is if you look at calendar, right? Multiple people are booking your calendar, all of them are leaders. There is a conflict in the calendar quite often. How many people have seen conflicts in the calendar? Conflicts in the calendar? Or people are sleeping? I don't know. Okay. Or maybe too boring a question. But that's the example of a multiple leader database, or your collaborative apps like Google Drive and stuff. So in Google Drive, multiple people are writing, so they are all connected to different databases and writing. But you can have a conflict. The way you get around that is, one extreme could be you lock the whole doc so that people can't write, exclusive lock. Other could be you take very small unit of work, for instance one keystroke, and lock just that, one row, things like that, right? But it's a little bit complicated. The other way to do it is you shard your database. So if you have 1000 rows, 500 here, 500 here, you do writes both the places, and then there could be replicas. ClickHouse does that. I have a diagram for that. Typically you do a last write wins or a quorum or something. So DynamoDB actually popularized multi-leader and implemented it in a way at quite the scale, and Amazon's AWS famous for sort of making things work pretty well. Actually a lot of companies depend on that, their correctness today. So if AWS went down, I don't know how many apps would be available, right? The day would definitely be screwed, but productivity will obviously go for a toss. So what DynamoDB does is there is no leader follower, it's leaderless. Basically, it's using quorum. So if you have 5 peers, you don't have leader and follower. Peers here, when you write and say my write I want 3 acts. So out of those 5 server, you got act from any 3 of them, and every row is versioned. So when I update, I have v2 of the row, v3 of the row, and stuff like that, right? So out of 5, 3 you got a act saying I wrote the latest version. When you do a read, if you care too much about consistency, so by the way, Dynamo is used in their cart and checkouts and stuff, right? So it has to be consistent there. It's a financial transaction. The conventional knowledge would say for your financial transactions, use your SQL database. They use Dynamo, right? Distributed, scales pretty well, NoSQL, every thing other than that, right? So when you basically go and read and you want to be consistent, you say I want 3 acts from my read. So out of 5, I will get a read from at least 3 of the nodes. So if you get 3, at least one of them will have the most updated one, right? It was only 5. 3 had responded yes to the right? You take the latest version and use that. At the same time, you could update the other one, so you can have a cron that updates the other one. But you got the latest version, 3 copies in the read, take the latest version. So storage engines, B trees and LSM trees. B trees, I think most people would have known. LSM tree is something that I'll cover more, but B trees are your sort of well adopted in MySQL or Postgres and Oracles of the world to get to sort of that specific place and read or update or whatever. Good for reads because you can just go to the random place. LSM trees are faster for writes because what you do is when there is a write, you just append at the end of the file. What is a database? At the end of the day, it's a file in your disk. It has to be making a promise that once you write something, you get it back, right? So you go to that file and write it at the end. Again, write it at the end. Even if you have to do an update, write it at the end, right? You don't go find it and change it. Just write it. So it's obviously are very fast. On reading time, you will have to do some sort of reconciliation, and quite well adopted, as you can see. I'm going a little bit faster given I only have 10 odd minutes or some grace if I can get, but I'll try to cover it. So what you would be worried, right? I'm just writing stuff one after the other, right? It will be too much data. My disk utilization will be too much. What you do is you have a segment of file here, you have another segment, and then you are merging here. Some cat-loving person, again taken from Martin Klupman's book and sort of color coded to explain it hopefully well. So you went and wrote yon 509, yon 510, yon 511, and hopefully this was okay. So when you merge, you are basically saying that I will look at all the versions and write the latest in the merged one, right? So once you have actually done your compaction, merging and stuff, your disk usage is less, and then you have only one copy, so you have some sort of consistency. And when you actually try to fetch something from the database or a streaming system or something, then you have your RAM, your disk, let's say this is the merged and compacted block using the same algorithm we saw in the last slide. In the index, you can't put every item there, so you want to make a sparse index and offsets in the compressed one. And by the way, beyond this compressed block, there could also be a block which is not yet compressed, the live data, right? And this is same across streaming systems, analytic systems, and stuff like Druid does that, Apache Vultr does that. So basically what we are doing here for read is you are looking for handiwork. Handiwork is not there in your index, but you know that if you do a binary search over there, this is sorted and this is sorted as well. Basically you are saying that it will lie between both of these, so you go to these offsets in the merged block, and within that you look for handiwork, and then there is that uncompressed unmerged block, you look there and then you get the last value from there. So I promised that I will spend some time on storage engine internals, the blocks that were there. Transaction manager is the one that basically schedules, coordinates, and tracks the transaction and the individual steps. Your lock manager is basically taking locks so that if there are concurrent writes to the database, right? So if you have a database, a lot of people are coming to the app. In Postgres, everything is a process. In MySQL, every client communication is a thread, so multi-threaded. in MySQL, multiprocess in Postgres, multiprocess in Apache Druid on analytics side. But log manager makes sure that when you are writing from multiple places, the data is not corrupted. An interesting thing that happens in the Postgres and MySQL of the world is that when you actually update, you are not, so there is a state of the database and there is write ahead log, right? You don't want to write to disk too many times, right? And you want to be fast as well, right? So you have a buffer pool, right? So in memory, what you do is you have pages describing the state of your data. You just go there and update that. But in the write ahead log, you actually for every transaction go within the begin and commit. Before commit, you have to go and persist it on the disk on write ahead log. For the database itself, you don't do it. The last bits of it will still be in memory. And for write ahead log, we use something called ODirect, which is a flag in the operating system to write directly. The pages in memory, the OS page cache, where things have changed after the last flush, those are called dirty pages. So you put on a dirty flag in those places. Those with dirty flag are batched, and OS, when it does a flush, it gets into the database, and then you uncheck the dirty flag. For concurrency control, there are a lot of ways: optimistic, pessimistic, multi-version concurrency control. In the interest of time, I will just cover multi-version concurrency control, MVCC. So if you look at Postgres, the way it does is every row, in fact, even in Postgres, will just go and at the end append a line. So if I have a row, I am updating it. At the end of the file, it will just write a row. The way you manage to get consistency there or safe concurrency there is, let's say the old row was written by the transaction x minus 1. The current version of the same updated row is x. So every transaction that was happening at that point of time was getting a copy of the older version of the row, which is x minus 1 transaction ID. This is something called xid internally. So the latest one is x. Now when you have committed all those concurrent transactions and this one also, then x minus 1 is marked for cleaning up in later, and x will be available for every transaction after now. If you know the vacuum process, that's what Postgres. How many of you have got troubled with auto vacuum process in Postgres? Okay, I expected Karthik to be there. Fine, some hands. So that's what it does. In a distributed setup, the way you do transactions is using two-phase commit. So you basically ask every database server to prepare the transactions in the first phase, and in the second phase, once all of them have prepared, there is some sort of confidence that they'll be able to execute it. Then you go and commit everywhere. There are more things there, but I am skipping it. Row versus column database, right? Row database, your transactional ones. Column database, your analytics ones. If you look at the top, country, product, sales, row 1, India chocolate 1000, right, is written in continuous location. Now if you know the file system, the lowest unit of thing that you can get out of the file system is the block, and if you just want first row together, then writing in contiguous location in one block will give you faster retrieval. If you want an aggregate over all the sales numbers in the columnar database, columns are stored together. You see the color coding here, right? So fetching by columns is faster there. Some real world databases. In the MySQL's case, you have, so we will take the concepts and then apply it here. So you have the master database called A. The one client creates the database, the other two do some insert, we'll put it in the binary log. The dump thread in MySQL master will send it over the network, IO thread will catch it, write it to something called relay log in the slave. And then the coordinator thread, which is single threaded, will pick up transactions one by one, and every worker will have a queue. They will enqueue it in the workers queue, and the workers will keep executing transactions. Obviously there has to be some concurrency here, otherwise it's a problem. So one of the ways you do concurrency is when there are concurrent transactions, they can be committed together. When they are committed together, they have same commit ID. That commit ID is written in the binary log or write ahead log in Postgres, and that goes to relay log. So the ones that have the same commit ID can be executed parallelly on the follower. A huge one, but to explain very quickly, you have your writes coming in batch of files, right? Batch data or streaming, even Kafka is supported there. So you write it, it goes to the router, then it reaches overload, which is only active passive, but this is distributed, you can have multiple of it. Every middle manager will spawn a JVM process called peons, or in the latest version there is something called indexer, which is multi-threaded. So they are moving multi-process in ingestion, like what Postgres is, to multi-threaded in indexer, which is like MySQL. This is where ingestion happens. Ultimately, this gets into segments, which are immutable blocks of data. Those are put into an object stored like S3 HDFS or something, and downloaded on historicals. Consider these are caches, so don't have to go to S3 every single time and incur cost. Those segments are kept here. So when the read comes to the router, broker will go take the historical data from the historical node. So the segments will be distributed here, and some of the latest data that's not been sent as segments will be here. Merge both of them and serve it. In a streaming system, you are basically what you're doing is a publisher is writing to a topic. There could be more topics, and the subscriber have interest in the topic messages. So you publish something, everyone gets it, right? Obviously, here what you want to do is you want to cache the latest data, so accessing them is faster. And if you really look for old data on the topic, imagine your cache was LRU. It will flush out all the latest messages across topics, put the old messages for a topic, and the whole system will become unstable, right? So that's why that happens. So costly to retrieve old data, use cases streaming and messaging. Multi-leader, right? ClickHouse, for instance, in this example, don't worry so much about the details. 1,000 rows, 500 on one leader, 500 on other leader, could have replicas, and all these processes are managed via something called either Zookeeper. In the latest version ClickHouse, this is a image taken from the document. There is ClickHouse Clipper, which is a drop-in replacement of Zookeeper, and there are some very good references. This is literally a photo from a drawer, right? So these are two books that I refer a lot. If you are more interested in this kind of content, you can refer these books. Some very good blogs. The first one is what I was talking of, and then some videos is Kafka database. Very provocative talk, very nicely articulated, and the couple of other links for Apache Pulsar internal architecture and Druid architecture. I have done those talks in some meetups. Those videos are what I have linked. Do I have a couple of minutes or something to take questions or offline? Okay, sure. Questions? And there are bonus slides, but then there's no time. I'll share the slides. It's there on my slides here link. Okay. Yeah, please. Yeah, please. Yeah.
Spoke about consistency.
Yes.
So you spoke about consistency, right?
CAP consistency.
Yeah, CAP.
Yes.
And I think it was more of an absolute sort of idea there, rather than say
linearizable consistency. Yes.
Yeah, rather than say a spectrum of say strong consistency versus eventual consistency, right? So we may or may not say that a database is inconsistent just because it has say asynchronous replication. You could probably say it is eventually consistent or strongly consistent, right?
Right. Like I said when I introduced the CAP theorem will not take you to the end. It will start a discussion. Right. Consistency, if you look at even Postgres and MySQL of the world, which you think of as consistent databases generally, even they don't implement linearizable consistency, right? The MVC databases. So if you look at, the point I'm trying to make is the one covered in the last blog there from Martin Klubman, where he says, please stop calling databases CP or AP. I think that's a good difference. But yeah, I mean, this is open. CAP theorem is, I think, always open to a debate.
Yeah, sure thing. Yeah.
But I agree.
It's about a spectrum.
Yeah. It's a whole spectrum, fine. But I also think that if you try to choose your database thinking CP and AP or consistency as CAP says, then I don't think you are making the right choices. Then you are probably not going deep enough. You have to look at what consistencies are there. Linearizable, serializable, eventual consistency. There are more, right? Yeah. Which one do you really want? And for that, you look at the database.
Yeah, some databases, they're like strongly and eventually. There are databases like, I work for AWS, so DynamoDB, and for Cosmos DB, for example, they're like 5 levels of consistency. So
correct. Even the streaming system, eventually consistent.
Yeah.
Right.